Hello, my name is Dan Cunningham, and I've been invited to give a talk on my favorite subject in mathematics, which is set theory. Um, and the title of the talk is the Schroeder-Bernstein theorem. This is a particular theorem in set theory that is of historical and actually mathematical interest. So I will also discuss some history behind set theory and give an outline of the proof for the Schroeder-Bernstein theorem. We all learned a little bit about set theory when we were in elementary school and high school, right? Intersections, complements. And you might initially come under the conclusion, that set theory is a very simple subject. Well, it turns out it does have some simple aspects, but it's a rather sophisticated subject. And perhaps I can convince you of that today. So let us begin. Okay, first I want to just mention, I'll sort of give an outline of what is set theory, and then also mention that one can view mathematics as just a sub-branch of set theory, right? So I use mathematics could be viewed as a subset of set theory using set theoretic language. Okay, here's the first question, right? What is set theory? Well, that's not an easy question to answer. But let me give you my synopsis of the answer to this question. I think of set theory as being the branch of mathematics that investigates infinity, okay? And I'll indicate that today. So it turns out set theory is a rich branch of mathematics whose fundamental concepts appear throughout mathematics. No matter what math course you take, you're going to be dealing with sets. So, and I also mentioned in this paragraph that almost every theorem in mathematics can be viewed as a theorem about sets. And so in a sense, all of the theorems of mathematics can be viewed as theorems of set theory, and that's what I outline here. And then the conclusion is, well, mathematics can be viewed as being embedded into set theory. That is, mathematics can be viewed as just a sub-branch of set theory. Now, that's an overblown view, but it turns out theoretically speaking, it's accurate. So let's go on to the next topic here. Now, as I said before, set theory investigates infinity. Well, there are two types of infinity, namely potential infinity and completed infinity, and I'm going to try to convey what that means today. Right? Potential infinity refers to a procedure that never ends. For example, look at this sequence, right? 0, 1, 2, 3, 4, 5, 6, it never ends. It continues without an end. And actually, mathematics is filled with sequences. So I remember in calculus, you talk about the limit of certain sequences. You never get to the limit of the sequence, but this sequence gets closer and closer to the limit. Okay, so for years, mathematicians just thought of this sequence as just a process that never ends. Now let us construct a set that contains all the items in this sequence. First, we'll put 0 in the set, then we'll put 1 in the set, then we'll put 2 in the set, then we'll put 3 in the set, and then 4 in the set. By the way, this just would continue forever. As a result, we'll never really be able to complete the process of constructing a set that has all these elements, and that's what I say here. However, since the sequence never ends, we will not be able to complete this construction. Well, that's the view of a infinity being a potential infinity. That is, you never get to the end. You never get to the end. Well, at some point, and mathematicians said, well, why can't we get to the end, right? And so that's what this notion of a completed infinity is. Imagine that one can complete the above construction, then this set actually exists. It is a mathematical object, right? The set consisting of an infinite number of members is a mathematical object, a set. And that's referred to as a completed infinity, right? It's an object that has an infinite number of elements. And this is actually a new, relatively new concept in mathematics, historically speaking. Oh, sorry. For centuries, mathematicians believed that the concept of a completed infinity belongs exclusively to philosophy or even perhaps religion, and does not belong to mathematics, okay? Now, let's talk about a little history behind set theory. In the late 19th century, George Cantor created and developed a mathematical theory of sets. He's also thought of as the godfather of set theory. Before Cantor, people did investigate infinite sets. When Cantor investigated infinite sets, then ever since his investigation, those investigations continued until today. So this theory emerged from his proof of an important theorem in real analysis. In his proof, Cantor introduced a process for forming sets of real numbers using an infinite iteration of the limit operation. Now, you remember in calculus, you compute limits, but you don't use the limit operation more than once. You evaluate the limit, get a number, and you go on to the next problem. But Cantor said, there's a way I can take advantage of taking an infinite iteration of the limit operation and prove a theorem about trigonometric series, actually. Cantor's novel proof led him to a deeper investigation of sets and of real numbers and to his theory of abstract sets. Cantor's creation now pervades all of mathematics and offers a versatile tool for exploring concepts that were once considered to be forbidden, such as infinity and infinite sets. Okay, and here's an abstract of what I'm going to talk about. First, sorry about that. What the hell's going on here? Okay, abstract. George Cantor stated a conjecture about comparing the size of sets. We'll talk about that. In the 1890s, Mr. Bernstein and Mr. Schroeder were the first to publish proofs verifying Cantor's conjecture about comparing the size of sets. As a result, the conjecture is now called the Schroeder-Bernstein theorem. And it turns out it's one of the first important theorems in set theory. It took a long time for someone to find a proof of this theorem, right? And you may be persuaded of that and when we talk about what's involved with the proof. I will discuss the history behind the theorem and present a proof that avoids any appeal to this thing called the axiom of choice. I will talk about the axiom of choice a little bit at the end of the talk. It's an important axiom of the set theory and in mathematics as well. I will end with a discussion on the axiom of choice and on the problems related to the Schroeder-Bernstein theorem. Okay, here's a table of topics, all right? So you might want to read these over. I'm not going to belabor them, right? So it just sort of specifies exactly what the topics I'm going to discuss. So let us proceed. Here are the main characters of our story. So this is a picture of George Cantor, and this is a picture down below here of Richard Dedekind. These two guys were not only worked together on mathematical problems, but they were very good friends. And it turns out Mr. Dedekind, and I'll mention this later, actually proved the Schroeder-Bernstein theorem before Mr. Bernstein and Mr. Schroeder actually proved that theorem, but he did not publish his proof until after they published their proofs. And as a result, these two guys get credit, and Mr. Dedekind was sort of lost in the distance of time. Okay, so now on the size of sets, what does that mean to talk about the size of sets? Well, initially, mathematicians just investigated finite sets, right? And so the size of a finite set is well understood. But let me go through this example here. The size of a finite set can be measured simply by counting. For example, the size of this set is 10, and the size of this set is 3, and the size of this set is 3. Moreover, the size x is a bigger size than the size y, right? Well, we can reach those conclusions just by counting the number of elements, right? Okay. Now here's what Cantor thought about. He was working with sets, of course, as we mentioned. Then he thought about this question. Can the concept of size be extended to infinite sets? Initially, when you think about this, it doesn't seem possible. It doesn't seem possible, but it turns out the answer is yes, it can be. Is there a way which does not involve counting of showing that two sets have the same size? Now, above here, we can decide that the set Y and the set Z have the same size, but just by counting the elements, right? But for infinite sets, you really can't count the elements. There's just, there's not enough numbers to count the elements. So is there another way which doesn't involve counting of showing that two sets have the same size? That's what we're going to explore now. Cantor was the first mathematician to seriously address and answer these questions. He observed that two sets A and B have the same size if there's a one-to-one correspondence between the set A and the set B. That is, one can evenly match the elements in A with the elements of B. And I'm going to follow that up with some examples here. In other words, Cantor realized that the A and B have the same size if there's a bijection. That is, a function goes from A to B that's one-to-one and onto. That's what a bijection is. So functional concepts come into play right away. Now here's a picture of a bijection, right? From this set A to this set B. And it's one-to-one and onto, as you can see by the arrow diagram here. What I want to sort of convey to you, if you have a bijection from one set to the other, you can use that to easily identify a one-to-one correspondence between the elements of A and the elements of B in this case. Well, for example, A corresponds to 5, B corresponds to 8. Well, we can actually list those correspondences. And here it is. As a result, we can use this bijection to construct the following one-to-one correspondence between the sets A and B. And so the elements match up perfectly. They match up perfectly, right? And so, so this is what Cantor observed. Notice we went through this process without talking about any numbers. Cantor declared then that we can conclude without counting that the sets A and B have the same size. Actually, this is the key ingredient that Cantor observed for finite sets. And then he said, oh, that surely must hold for infinite sets as well. So let's look at an example of that. Here's the set of natural numbers. I include 0 as a natural number. And so this is the set of natural, which is an infinite set, right? And now let's look at the set of even numbers, right? So this is the set of even natural numbers. This is also an infinite set. Now, you might, initially, the early mathematicians said, well, this set is missing 3 and 5. And so this set has fewer items than this one. So the set N should be bigger than the set E. Well, when you're dealing with infinite sets, the obvious doesn't necessarily hold true. But anyway, so Cantor said, hey, let's look at this bijection from the set of natural numbers to set E. F of n is equal to 2n, right? 0 goes to 0, 1 goes to 2, 2 goes to 4. Oh, it turns out there's a one-to-one correspondence between these two sets. Let's visualize that one-to-one correspondence. So here's this one-to-one correspondence because we have a bijection from the set of natural numbers to the set of even natural numbers. Here it is, 0 corresponds to 0, 1 corresponds to 2, 2 corresponds to 4. There's a one-to-one correspondence. And so Cantor then realized as a result that because there's a one-to-one matchup between the elements of the natural numbers and the elements of E, then Cantor concluded that the two sets have the same size without numbers. So these two sets, Cantor observed, well, this set has the same number of elements, same size as this element without numbers. When I say the same number of elements, that's really a misspoken. I really should say the same size. But I'll tend to do that anyway because I have that oversight. Cantor then proved, here's a strange thing. The set of rational numbers you think as being much bigger than the set of natural numbers because there's so many more of them on the real line, for example. But Cantor proved the set of rational numbers has the same size, same cardinality as the set of natural numbers. That was a complete surprise. Mathematicians were very surprised by that result. I mean, at least the mathematicians that were interested in Cantor's work initially. Cantor then conjectured that the set of real numbers also has the same size as the natural numbers. So, by the way, so it looks like the set of rational numbers have the same size as this set. So you would think any infinite set should have the same size as this set, right? But it turns out Cantor thought that too initially about the set of real numbers. He said, well, since the set of rational numbers is the same size as the set of natural numbers, it seems obvious to me that the set of real numbers must have the same size as the set of natural numbers. So he conjectured that because it seemed obvious. Now in mathematics, of course, Just because something seems obvious doesn't mean it really is obvious. In fact, it may be false. It came as a complete surprise to George Cantor when in literally the year 1874, he discovered that the set of real numbers is much larger than the set of natural numbers. This unexpected result would have an enormous impact on the future of mathematics. The mathematics we study today is impacted by Cantor's work. You may not see that directly, but it's actually true. Some of Cantor's contemporaries, oh, here we go. These are the people, the skeptics. Cantor's contemporary skeptics refused to acknowledge his mathematical discoveries. For example, Poincare, he's a famous, I think a French mathematician, referred to Cantor's work as a grave disease which would infect mathematics, kind of like the COVID virus is going to infect mankind, right? It turns out Cantor's work did infect mathematics, but it had an evolutionary advance effect. It made mathematics richer and more interesting. Cantor's accomplishments would eventually be recognized. So here's some accomplishments. In 1904, the Royal Society, which is a famous society in England, presented Cantor with its prestigious Sylvester Medal for his brilliant research. So there were mathematicians who recognized Cantor's achievements. David Hilbert, another famous mathematician, described Cantor's work as the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. Cantor was the first to explore the infinite using mathematical concepts. And apparently he was the first to do that. Okay, so now we're going to investigate some of Cantor's definitions on comparing the size of sets. Okay, so rather than say the same size, mathematicians usually refer to two sets having the same cardinality, right? But what does it mean to say they have the same size? Well, we already talked about that. That means A and B have the same size if there's a bijection, that is a one-to-one onto function from the set A to the set B. And here's the fancy terminology we're going to use to represent the fact that there's a bijection from F to B, from A to B, excuse me. And notice that this has an equality, but there's a little C there, and that stands for cardinality. You could read this as saying A and B have the same cardinality. And that's what I say here. The expression here is not an equation, right? Don't think of it as an equation, but unfortunately it looks like one. But it's an expression that means there's a one-to-one function from A onto B. And that was Cantor's initial definition of having two sets having the same size. And then Cantor went on to say, well, if I now know what it means for two sets to have the same size, what does it mean to say one size is smaller than another size? One set has size smaller than another set. Well, here's his definition. The cardinality of A, the size of A, is less than or equal to the size of B. And here's the notation that one uses. If there's an injection, that is a one-to-one function from A into B. So that means if you have a one-to-one function from the set A to the set B, we can then conclude that the set A has size less than or equal to the size of B. And that's what this notation means. Again, this is not the inequality symbol of the real numbers, right? This is the same symbol, but it's used in a different context. What does it mean to say that one set has strictly smaller cardinality than another set? Well, here's what Cantor came up with. A set A is strictly smaller than another set B in size, and here's the notation that's used, strict inequality there. If there's a one-to-one function from A to B, and at the same time, there is no function G from A to B that's both one-to-one and onto. That's what it means that one set has smaller size than the other. Again, we're not using numbers at all here. That's Cantor's observation. You don't need numbers to talk about the size of sets. So now we're going to talk about three theorems and three conjectures due to Cantor. So Cantor's theorem, well, Cantor said the set of natural numbers has the same size as the set of integers. And he also proved, as we mentioned before, that the set of natural numbers has the same size as the set of rational numbers. Now, initially, of course, mathematicians found this to be quite bewildering. but later on they learn to accept it, right? Just because your intuition fails or refutes your belief in something doesn't mean that something is actually false. Okay, now here's what Cantor proved, as we mentioned before, the set of natural numbers is strictly smaller than the set of real numbers. That is, there's a one-to-one function into the real numbers, but there's no one-to-one and onto function from natural numbers to the real numbers. And then here's something surprising. I'm sorry, my mouse is very fussy. It says there is a set, not only is the real numbers bigger than the natural numbers, but Cantor said after I proved this, hey, there's a set P which is even bigger than the set of real numbers, right? So there's a set P bigger. This came as a real surprise too. But after he proved this, he said, why should we stop there? He said, Cantor then showed that there's a sequence of larger and larger infinite sets. So there's a set bigger than the real numbers, and there's a set bigger than that set, P. And then there's a set P2, which is bigger than that set. And this goes on without end, without end. Thus, there are infinitely many different infinities. Now, this came as a complete shock, of course, to mathematicians at the time. It just seemed like this was going more philosophical than mathematical, but it truly is mathematical. Okay, now we're going to talk about some conjectures of Cantor. This is actually a famous conjecture in set theory called the continuum hypothesis. You may hear that term in your future endeavors because it comes up now and then. Anyway, here's what it says. Let's look at this. Right here. Let's look at this. We know the set of natural numbers is strictly smaller than the set of real numbers. Then Cantor said, well, wait a second. Is there somebody in between these two sets in size? Is there a set A that is strictly bigger than the natural numbers and at the same time strictly smaller than the set of real numbers? Well, that's what the continuum hypothesis says. It just serves, it's a conjecture. We don't know if it's true or false. So here's what Cantor said. Well, I conjecture that there's no set of real numbers, A, whose size is strictly between the natural numbers and the set of real numbers. And it turns out this was a very difficult conjecture. No one was able to actually prove it. And in a sense, it's still an open problem. In a vague sense, I should say, but I won't go into more detail. Then there's this other conjecture. He says, given any two sets, one is going to be has size less than or equal to the other. And that's what this is, the comparability. So for any two sets, we can decide which set is bigger than the other. And that turns out not to be, it seems obvious, right? Because it reminds us of the ordering on the real numbers. But it's not obvious that this is true or false. And here's another conjecture by Cantor. And it's called the anti-symmetry conjecture for sizes of sets. So let A and B be sets. Then it says if A is less than or equal to in size to B, and B is less than or equal to in size of A, then they have to have the same size. Now this seems pretty intuitively clear, right? And you might think, well, it's probably true. In fact, it is true, right? It is true. And you might think, well, it should be easy to prove. Well, it turns out it's true, but it's not easy to prove. Okay, here's the Schroeder-Bernstein theorem. The Schroeder-Bernstein theorem says the anti-symmetry conjecture is actually correct. Here it is. It says if A is less than or equal to B in size, and B is less than or equal to A in size, then the two sets have the same size. Now, Cantor had he proposed a proof of this theorem, but his proof used an assumption that was not, it was shown to be a little unnecessary assumption. But Schroeder and Bernstein had proofs that didn't use Cantor's assumption. So sometimes this is called the Cantor-Schroeder-Bernstein theorem. But I like to call it the Schroeder-Bernstein theorem because these are two guys that first published the proof. Okay, so Schroeder and Bernstein published their proofs in the 1890s. Okay, and the earliest proof of this theorem was due to Dedekind, our friend Dedekind, and Cantor's friend as well, in 1887. Notice he actually proved it their proof was published in the 1890s. He proved it in 1887. I don't know when these guys actually proved it, but it took them a while to publish it. It usually takes several years to publish a paper. Okay, but it was not published formally until 1932. So Dedekin's name is not attached to this term at all because of his tardiness in publishing his paper, I guess. Okay, now Zermelo is another mathematician of repute in this topic, published a new proof in 1908. And the proof that I'm going to outline and discuss today is, I think it's due to Zermelo. I think it's the simplest proof of all the proofs of the Schroeder-Bernstein theorem. But I'm not speaking with complete knowledge there, but I think that's the case. Now, there are over 30 different proofs of this theorem. Which one is easy? Some of them are kind of tricky and mind-boggling, but others are a little more accessible. So before I go into the proof, I want to revisit a concept that hopefully you've seen before, called the image of a set under a function. Let me talk about this. So let F be a function from a set A to a set B, and let's pick S to be a subset of A. Then this notation, F square bracket of S, is called the image of S and is defined by this. So let me just highlight this right here. Let's just look at this part here. So this is defined to be the set of all objects, the values you get by taking elements from S, plugging them into the function F, and then evaluating, then form the set of all those values. And so here's a picture of this. So here is the set S. So you take all these elements in S, you plug them into F, you'll get a value Y over here. And you collect them all together in a set, which I denoted by this rectangle. So it starts off with a subset of A, and the F of square bracket of S is a subset of B, right? That's called the image of a set under a function. Okay, so we're going to use, this concept comes into play, and so let's move on now. Now, this is a key lemma that's used in the Schroeder-Bernstein proof. So let me talk. I don't write a proof of the lemma here. The proof uses some set theoretic principles. It's not difficult, but it's a little too long to put in a discussion like this. But here's what it says. I have a picture to convey what it says. Okay, so here's what it says. Suppose you have a function from A to B and G from B to A. Notice I don't presume that they're one-to-one or onto or anything. It's just two functions that go from the set A to B, and G goes in the opposite direction from B to A. Then there is a subset X of A such that this equality holds. Now this is G of an image, and this is F of it, the image of F under X. It looks kind of like a crazy equation, but let's look at the figure here. It explains what it says. So it says, the lemma says there is a set X, subset of A. Here's the subset of A. And so, well, if you take the image of X under F, you'll get over here. So this is the image of X under F. Take the complement of that in B. So here's the complement of that in B. Now take the image of this under G, and you get back. It turns out this is the image of this set, subset of B under G, you get this. And it turns out A is completely covered as a result of this. Okay. Now, it's not obvious that this is true, by the way. This is not an obvious result. It's kind of surprising because, first of all, F and G don't have to satisfy any special properties of them being a function. So when I first saw this, I thought it was quite amazing. But once you see the proof, you sort of believe it, right? Sort of believe it. Okay, so let's take this for granted now. And this picture will be useful for talking about the proof of the Schroeder-Bernstein theorem. So let me move on here. Sorry. Okay, here's our discussion of the, oh no, I beg your pardon. Here it is right here. So here's my discussion of the proof of the Schroeder-Bernstein theorem. Assume, well, okay, so first thing, we're assuming that these two things hold. Then I say, okay, what does that mean? Well, that means there's a one-to-one function from A to B, right? That's what this first one means. There's a one-to-one function from A to B. And this means there's a one-to-one function from B to A. So I just write that out explicitly, right? So here's a function from A to B and a function from B. Hey, this is just like the lemma. But we're assuming in this case that the functions are one-to-one. Okay, so by the lemma, it says there's a subset x of A that satisfies this equation. And then I mentioned, see the previous figure. And I'll go back to the figure in a moment. Okay, well, then it says it turns out since G is 1-to-1, it has an inverse function. Now, you may not be real familiar with those concepts, but you'll see those concepts in your future courses. But let's go back. So G has an inverse, but let's go back and take a look at the picture I have here. So I want to define a function now from A to B that's 1-to-1 and onto, that's different than F and different than the inverse of G, for example. Here's the definition that works. Turns out it works. You have to read the proof to be convinced that it actually works, but I'm just telling you, here's what it is. So we want to define a function from the set A to the set B. Here's what we do. Well, if we have an object that lives in this part of A, the X part of A, then we define the function to be, hey, just the result of plugging in F of that individual over here. Then if we have an individual who lives over here, how am I going to define the individual who is over there? Well, you plug that into the inverse G function, and you get an individual over here. It turns out if you do that, because of this equality here, then the function is 1-to-1 and onto, then you'll have a bijection. So here's how it's defined. Since G is 1-to-1, the inverse function G inverse is also 1-to-1, and the domain of this function is the range of G. Now, these are set theoretic function concepts that you may be familiar with. Okay, then here's the definition of this function that I just mentioned. So if little x lives in the set X, you just plug that into F and get your value. If X lives in the complement of X on the other side of X in A, you plug that into the inverse function and there's your value. And it follows, it's not obvious that it follows, by the way, that H is a 1-to-1 and onto. And other proofs of this theorem are a little more intricate than this one. Now let's look at some corollaries of this result. Now this is a surprising result, at least it was initially. Now it's not so surprising to mathematicians anyway. It says the unit square has the same size as the unit interval. What? Mathematicians, when they first, Cantor actually, this is a corollary of the Schroeder-Bernstein theorem, I might add. But here's a picture of it. Okay, and Cantor proved this theorem. He said, after discovering the proof of this corollary, Cantor exclaimed to his friend Dedekind, I see it, but I don't believe it. Because it was counterintuitive, but here's the picture to sort of convey why it's counterintuitive. Cantor proved that the number of points in the unit square here is exactly the same as the number of points on the unit interval here, right? It looks like there's many more points in this unit square than there is in the interval, but it turns out that's not correct. There's exactly the same size. The set of points in this interval has the exact same size as the set of points in this interval from 0 to 1, well, the open interval. And then, okay, so Cantor was able to prove that, but hey, it turns out Cantor went beyond that after establishing that. He actually showed that the set of points in the entire XY plane has the same size as just the set of points in the open interval between 0 and 1. Now that seems just bewildering, but it's true. Cantor's ideas were very potent and allowed him to reach all sorts of conclusions. So now I want to sort of move away from that topic a bit and talk about this thing called the axiom of choice. Now, you may, in some of your math books, you'll often see references to the axiom of choice. So I thought I should just talk about what it means a little bit. So an important and fundamental axiom in set theory is called the axiom of choice. It's also an axiom in mathematics in general. Here's what it says. Suppose you have a sequence of non-empty sets. This denotes a sequence of non-empty sets. So A sub I are all the sets, and they're indexed by elements of this is called the index set. So you just have a bunch of non-empty sets A. Then it says there's another sequence indexed in the same way, such that xi is an element of each of A sub I individually. So it seems like sort of an obvious thing. If these are non-empty sets, and of course each one of them has elements, but this says you can pick elements from all the sets at the same time, more or less. That's what it says. It's a simple axiom, but it turns out it has deductive strength that's hard to believe. So this axiom was first formulated by Ernst, Zermelo in 1904. And the axiom of choice is used to prove many theorems in mathematics. And for example, in real analysis, there's a theorem that says that a function from reals to reals is continuous at a point if and only if for every sequence of points that converges to C, then the limit of that F sequence is equal to F of C. It turns out the axiom of choice is used to prove this theorem in real analysis. This is actually sometimes used in calculus too. So the axiom of choice is everywhere. It's everywhere, even though you may not see it. Many times mathematicians apply the axiom of choice and they don't realize they're actually applying it. So sometimes it's thought of as an invisible axiom. Okay, the axiom of choice is also used to prove that every vector space has a basis. When I first learned that, I thought that was pretty amazing, but I'm easily amazed, right? Problems related to the Schroeder-Bernstein theorem. Okay, so this ends our talk here. Okay, so we know that from the Schroeder-Bernstein theorem, if you have a function from A to B that's 1-to-1, and a function from B to A that's, B to A that's 1-to-1, then you know the two sets have the same size. Now, what happens if you just have a function from A to B and B to A that are both onto? Can you conclude that the two sets have the same size then? It's not clear. It's not clear. Okay, here's another open question. Well, open for us, all right, but it's actually been settled, but it's a good thought problem. Excuse me for my bouncing around. Let F be a 1-to-1 function and let G from A to B be onto. Okay, so this function goes from A to B, it's 1-to-1. And this function goes from A to B and it's onto. Do these two sets, can you conclude that they have the same size? It's not clear, it's not clear. But it turns out using the axiom of choice, you can prove that both of these are true. Then I'm not sure, is there a proof that doesn't require the axiom of choice? The Schroeder-Bernstein theorem doesn't require the axiom of choice, but do these actually require the axiom of choice? And no, I'm not sure. I'm pretty sure that's true, but I'd have to think about it and investigate it. Now, let me just do some self-promotion here, right? If you really want to see proofs of the things I talked about, they're in this textbook called Set Theory First Course. And it's pretty reasonably priced. Anyway, if you have any other questions, just come and talk to me. My email address is at the beginning of this talk, and if I go back, it'll take a half an hour. Okay, thank you very much. Farewell.